I'll just share my screen. Huh?
Yep, if you could get your slides ready, I'll just go over a few housekeeping rules. Okay, so hi everyone, hello. If this is the first time you're joining for our webinars, welcome. Let me start by going through a few housekeeping rules with regards to these webinars. So today we've got Anne and Michelle who are going to be presenting. Sorry, I use 3 screens, so I may not be looking directly at the camera. Let me change, there we go. So today, what we'd like to do is we're going to have Anne and Michelle presenting today. And we've got Anne's screen here. So we're going to have Anne and Michelle presenting today. As the attendees, your audio and video has been disabled. If you do have any questions throughout the presentations, you're more than welcome to write a question for either of them. Please do make sure you indicate if the question is for Anne or for Michelle. And you can write your questions in the Q&A box, which you should be able to see at either at the bottom or at the top of your screen. There's a Q&A button, and you can click that and it'll come up with a pop-up box where you can type your questions in. You can also, at the end of the presentations, verbally ask your questions. If you do want to ask a question, please raise your hand. So when you click on your participants box, you should be able to see a new pop-up box come up, and there'll be a little button that says raise hand. So if you do have a question, raise your hand. I'll see that and I'll flag that with Anne and Michelle. If you do have any troubleshooting questions, you can alternatively use the chat box. So please use this chat box at the bottom of your screen or at the top of your screen. And you can write your question there. I will be looking at this box specifically. So these are solely for troubleshooting questions, so things that are technical, that are unrelated to Michelle and Anne. And that's about it with regards to the housekeeping rules. If you do have any questions and you're not sure where it should go, write it in the chat box, and then I'll be able to direct you, and I'll be able to flick that onto Anne and Michelle as well. So I'll hand over to Anne now.
Okay, thanks Michelle. Hi everybody. The way we've structured this morning is for me to talk for about 20 minutes, just to give a general overview of the area and introduce you to the various models for trajectory analysis. And a lot of these slides will just be pointers of where to get more help, because the area is big and the terminology is quite confusing. So there's a lot of references within these slides, and I've made up the slides will be available, and I've also made up a Word document with a list of all the references that I will allude to in the talk. So to get started, and after I've spoken for 20 minutes, then we'll hand over to Michelle Tew, who's been doing some latent class growth analysis on quality of life measures over, I think, 5 years after total knee replacement. So she's going to give an example of the application of the one of the particular models, and an overview of the various decisions she had to make along the way, which will kind of help you if you would like to apply the same techniques to your research. So, trajectory analysis, what is it? It's a bandied about term which basically means any looking at change over time in variables that we collect from individuals. And so a lot of the terms that you'll hear used are time trends, time paths, time course, life course, growth curves and trajectories. And you'll often hear the term growth curve models, which is really the same as trajectory models. And what these models seek to do is to model differences between groups of people in the within-person changes over time. So the individual pattern of change over time is modelled, and then we're looking for how do those particular trajectories of individuals, how do they differ between groups of people. And there's various ways of doing that, of which latent class trajectory analysis is just one. And because the field is it's grown up over a number of disciplines, including epidemiology, social sciences and psychology. So, and they've all had like a different heritage. So often the language is quite different, even though people mean the same thing. So I've tried to give you a bit of a roadmap there as well through this talk. So we say trajectory models, but many people talk about growth curve models, and they're the same thing. Again, just modelling that between-person difference in within-person change over time. And the reason that I've found the latent class model so helpful, and we'll get into this a bit more detail in a minute, is that often we're dealing with very complex life course models where changes in a number of constructs can occur and interrelate to affect health and disease. And at some stage, it's the job of the biostatistician to try and distill down the very complex model on the left into what we call a directed acyclic graph, or an epidemiological kind of roadmap for your analysis on the right. And sometimes that's really hard to do if you've got a lot of variables that you have over time in different constructs. And I've worked a lot with the RAIN study over here, which is a longitudinal birth cohort study of people born between 1989 and 91. And we have many repeated time measures on these people. They're now 28 years of age. And so I've found particularly these latent class growth models to be of use in getting to some of the more, or addressing some of the more complex hypotheses that we have. But the choice of method, latent class trajectory analysis isn't always the best choice. And so your choice of method should really be guided by your research question and your understanding of the field and its underlying mechanisms. And we often see this problem that something that's gets to be a bit of a fad in statistics, it's easy to apply, and people start letting the tail wag the dog and use that method for everything. So just try and be mindful about whether some of these techniques that I'm going to talk about are really the best one for the job, or if something else would be better. A good discussion of this is the International Journal of Epidemiology had a special issue in 2016, particularly on life course epidemiology. And life course by nature is repeated measures over time of various things. So they have quite a good issue with various approaches to modelling that kind of data. And particularly the commentary, the editorial commentary, is good to read. So when we think about trajectories, we can do a number of things with them depending on the research question. So we can simply just describe the time course or the life course of a factor. So it just may be of interest to see, you know, on average, what happens to people after total knee replacement, how long do they take to get to maximal improvement, and so forth. We can use a trajectory variable as an exposure variable that we think might influence a future outcome. So in particular here we might be looking at trajectories of psychological, examples I can think of are modelling trajectories of psychological dysfunction over childhood and how that may relate to future social or health outcomes in adulthood. We can use the trajectories as outcomes. So a number of research questions that we've done have looked at early life factors, how they've influenced trajectories of pain or disability through childhood and adolescence. We can think about trajectories of things as confounders or moderators of relationships between other variables. So here we might think about how does a person's a trajectory of overweight or obesity over childhood and adolescence, does that moderate the relationship perhaps between physical activity and health later on? And then we have parallel processes where we might want to relate one particular trajectory to another, and I'll give you an example of that later that we've done. So heads up, the terminology is really confusing in this area, and as I said, it kind of depends upon which particular discipline that you've evolved from as to which terms you find confusing. So, one paper that's I found particularly helpful is this paper by Curran, 12 frequently asked questions about growth curve modelling, because there are kind of two underlying approaches, if you like, to modelling change over time. And one is what we call a multi-level model framework. And you'll hear that referred to as mixed models, hierarchical models, random effects models, or multi-level models. And they're all the same thing. I'll explain that a bit more. Then we have structural equation models, which are a slightly different paradigm of doing what's essentially the same thing, but there's some differences in the way those two things are applied. And then on top of that, we can have latent class trajectory models, and both structural equation models and multi-level models can be extended to latent class models. Something that you'll commonly see utilised when we're looking at life course or time course data is regression with generalised estimating equations. I won't discuss that today, but if you have questions about that, I do have a lot of resources on that and how the points of difference from these other techniques that we're discussing. So just before we get on to latent class models, I just want to just make clear the two underlying different approaches. So when we think about a mixed model or a multi-level model over time, we have these time points here, which we're modelling with a main effect, which is what we term the fixed effect. So that's on average, how does the group change over time? But then we can acknowledge within the model that there'll be variation around that average effect. So each person will have a different starting point, and we can also make the model so they have a different slope over time, so a different rate of change. And so that's where our term random effects come from. So this variation over the starting point is the random intercept, and the variation over the slope for time is the random slope. And we can make that even more complex by adding polynomial terms or like squared terms or cubic terms to get different shapes in the trajectories. There's a lot of different ways that you can do that. But that just gives you a kind of understanding of what a fixed effect versus a random effect is. So, for example, this is an example of a random effects model where we haven't done a latent class random effects model. We've just done a mixed model where we've modelled a different trajectory for people after bariatric surgery that have had either a gastric band or a sleeve gastrectomy. So we can group people according to some known group, which in this case is band or sleeve, and then plot the average trajectory for those groups, and then look at how individual trajectories within those groups might fit or not fit those particular mean trajectories of the groups. So there's very many applications where we don't have to move to a latent class model, which I'll talk about in a bit, and we can just model our time according to our covariates, so our changes over time according to our covariates that we know about, and ask, are there differences over time between these known groups? This kind of model is commonly used in the analysis of randomised controlled trials with multiple time points. So this is an example again where we've modelled changes over time, this time with time as a categorical variable, and we've asked the question, is there a difference over time between our two treatment groups, our usual care and our cognitive functional therapy, people with low back pain? So we can see both groups get better, but on average, the cognitive functional therapy group get better, but then there's no difference at 12 months. So this is using a mixed model where each person in this model would have a random effect for their intercepts and slopes, but we're just interested in the main effect, and that is the randomised groups there. So if we move from a mixed model to a structural equation framework, this really arises out of the psychology and sociology literature that tend to use this a lot, and also economics people. And here we consider these measures of, this is a body mass index over time at time 1, time 2, time 3, up to time 9. We consider them indicators of the underlying latent variable of the intercept and the slope. So just like on this previous model, we had this random intercept which allowed between individual difference in the starting point, and a random slope which allowed differences in individuals over time. The structural equation model does the same thing, but it's really confusing because they call these variables latent slope and latent intercept, but then we have to talk about latent class growth models, which is a different thing again. So just remember, within a structural, if you're reading papers with a structural equation model, they'll be estimating these latent unobserved variables, which are the same as the random effects in mixed models. So they're the two underlying paradigms for moving into latent class analysis of differences or changes over time. So we just shift now to think about latent class analysis and what that is. What that is trying to form subgroups within your data of people who share common characteristics of the stuff that you're interested in such a way that the people within the subgroups are similar. So they look similar across those variables of interest, and the difference across those variables of interest is maximised between the subgroups. So it's trying to maximise difference across people and, form different groups of people according to a particular set of variables. And that doesn't have to be time variables. So we can, subgroup people according to all sorts of different profiles. So, commonly we can subgroup classes of disease according to various test results and symptoms and so forth. So latent class analysis is a form of grouping procedure which is part of a family of what we call unsupervised classification procedures. So we're basically just asking the data what subgroups naturally emerge here. So we're not trying to say, are males different from females, or is this particular disease different from that disease? We're just saying, giving the system some data and asking, are there subgroups that naturally emerge based on those data? And latent class analysis is only one way of doing that. And the other main way of doing that is what we call the distance-based analysis procedure, where if you can imagine a scatter plot in multi-dimensional space, we look at distances between points and group people, like galaxies. We group the stars together. The people would be grouped. The points representing the people would be grouped where they were close together in space. But latent class analysis does that same grouping procedure based on statistical criteria. And the advantage of that is that we get a probability-based estimation, which allows us to not have to definitively assign a person to one group or another. So we could have a person that's maybe 90% likely to lie in one group, 10% likely to lie in another, because their data is really close to the centre of one particular group. Whereas someone may have a 60-40 chance, and so we can kind of account for that uncertainty in subsequent analyses if we use latent class analysis as a grouping procedure. The other advantage that it gives us is that it allows a better judgment as to the number of underlying classes or subgroups that actually exist. So because we get this probability-based maximum likelihood estimation, that gives us some statistics we can use to choose what's the most likely number of underlying classes in the population. It also handles variables of mixed type, so we can have a model where we have the indicator variables forming our groups can be binary or continuous or ordinal or a mix of all those things. And it handles missing data well, because it can handle data that's missing completely at random. And it also provides us, as I said, with classification probabilities. So each person would end up with a probability of membership for each of the classes. And then in subsequent analysis, we assign a person to the class for which they've got the maximum probability of being a member. So that's latent class analysis. And latent class trajectory analysis groups people by common patterns over time. So that's the key. And within that, there is a number of subclasses of latent class trajectory analysis. And I'll go through these one by one. The first simplest one is just what we call a repeated measures latent class analysis. So the variables that we're subgrouping on are just the observations of the variable interest. So it would just, I use that example of body mass index. So we'd just be classifying based on the body mass index over time. Whereas if we move to a latent class growth analysis, now we're classifying people according to their measure on that intercept and that slope. So that graph that I showed you where people could have a random intercept and we'd have a random slope. So it's those values that are being classified, not the actual BMI measures. And then the further extension of that is latent class growth mixture models, which is the same as latent class growth analysis, but it models some variation within the classes, which we'll get to in a minute. So, very complex area. For a great review of the difference, this paper here is reasonably simply written paper, which I think, you know, would be understandable by non-statisticians. So, latent class growth analysis is particularly useful when there's very different patterns over time, when there's complex patterns of change over time, or to make summary variables of trajectories where you've got a really, you know, a very complex model with a lot of other variables that you need to consider. So if I just flick back to this, in this kind of situation where we're using a mixed model, we're assuming that everyone can reasonably fit around a common mean trajectory, and we might make groups of those mean trajectories according to known covariates. But the fundamental underpinning is that everyone follows a similar trajectory. That's pretty good for certain things, like certain growth parameters, such as perhaps weight loss after surgery or BMI or so forth. But for some things, it doesn't fit so well. And I'll show you a couple of examples there. So latent class growth analysis or latent class analysis is particularly good, where you've got very different or subgroups with really different patterns of change over time. So you don't have that underlying assumption that everyone's roughly following the same pattern. There's just variations on that single pattern. So the first type of latent class trajectory analysis is this repeated measures one, and that classifies people by their patterns of observation over time. So there's no growth parameters that are fitted. So we're not classifying or subgrouping people according to their random intercepts or slopes. We're just classifying them according to the observations that we've seen. So it's useful if we've got lots of up and down changes, we have concerns about whether we can fit the shape of time well, or if we have separate measures of things. So here's an example where we use this technique. So this looked at the incidence of low back pain in the RAIN study over 3 years of data at age 17, 20 and 22. But we didn't only have information about whether they had back pain, we also had information about the impact of that pain. So they were asked questions around whether they sought professional advice, that they'd taken medication, missed work or school, had low back pain interference with their normal activities or physical activity or recreation. And so we had this quite different variables, and we had them repeated at over 3 points in time. So we used a simple repeated measures latent class to group people into 4 different groups. So you'll see here that on the x-axis are each question that they were asked around if they had low back pain at 17, and then questions about impact here. Did they seek professional help, take medication and so forth? And then on the y-axis is the probability of them doing each of those things, having back pain or having each of those impacts. And so you'll see the model that was chosen as the best fit was a 4-group model with the lowest cluster, or the low values, or which was the most prevalent cluster of 53%, who had very low probability of having low back pain at any of those time points and no impact from that low back pain. In contrast to this high pain and impact cluster, where at each time point their prevalence of pain was very high and their probability of having some kind of impact from that pain was also high. So this model was helpful in that we could use these quite varied what we call indicator variables that you see along that x-axis. And this is just the data presented in a different way, where instead of that those time plots, we can see the high pain and impact trajectory, and this is pain in the last month. So the high pain and impact trajectory had high prevalence of pain. They had high prevalence of taking medication, interference with normal activities and so forth at each of the 3 time points, 17, 20 and 22 years. This is another example of a repeated measures latent class analysis, and this is by Alice Kongstead and Peter Kent, who's an AI in the OPUS CRE. And they took people who had presented with acute low back pain to their GP, and then these people reported by SMS on their low back pain status each week over the coming year. And they then grouped them on those 52 repeated measures, and you can see that there's a lot of fluctuation there. And so the best type of model for this was a repeated measures model, which allowed that capture of very complex patterns over time in between the groups. So the latent class, the extension to the repeated measures is what we call latent class growth analysis. So this applies it subgroups people according to those growth parameters. So if we go back and think about that random intercept and that random slope over time, and then other functions of that time curve can also be used as the subgrouping variables. This can be implemented by this procedure written by Daniel Nagin called TRAJ, which is implemented in SAS and also available in Starter and R, and you can download it from this website. You can also do this technique in M+ and 8 latent gold. And it's a little bit more flexible within those softwares. So Michelle Tew is going to talk much more in depth about her experience with this, and because I'm kind of run over time already, I won't spend too long on that, other to say that the procedure allows us to model time as change over time in a variable according to polynomial functions of time. So we can get curves and we get S patterns with this technique, and group people who into groups that have very different patterns of change over time. If you're using Starter, then this particular reference by Jones and Nagin, it's very useful for you to get started and very readable. We can model different types of data in that TRAJ procedure, and we have even more flexibility with other programs. This is an example where I moved to latent gold software because we were looking at differences in knee pain score, which was an ordinal variable in people who had had a total knee replacement over 5 years. So we use their pain score as an ordinal variable and time as a nominal variable to model 3 different trajectories, people that had a big improvement in pain and, a 50 is a good score, to very mild pain, and 10, 20 is a poor score with moderate to severe pain. This is just another example of the same thing, television watching. I'm just skimming through because of our time. Again, you can go to these papers to see the detail. Michelle will talk a lot about this. These are all the choices that you have to go through. So Michelle will be talking more about that. A nice extension of latent class growth analysis using the TRAJ is that we can do these dual trajectory analyses where we might model change in one thing over time and relate it to change in another. And this is something we've just done in the RAIN that's not unpublished as yet, where we've looked at changes in body mass index over time between 14 and 22 and related that to changes in C-reactive protein over time, which is a marker of inflammation. So what the model does is relates this trajectory membership to the one on the right, and you can see that via the graph below. So if we look here on the left, the underweight group, which is the group in the blue on the left-hand graph at the top, they have a far more likely probability, or much higher probability, of having a stable low C-reactive protein trajectory, whereas the high overweight to obese group are far more likely to have this green trajectory here of a high CRP trajectory, or more inflammatory system. So the extension to the latent class growth analysis that I've just spoken about here is that once people are assigned to a particular group, the assumption is there's no additional variation in that group. So everyone follows that trajectory, and any difference between people within the trajectories is just about random error and not true difference. And this is the main reason why this particular application is not hugely popular among classic or among biostatisticians, is because many people feel that this assumption is untenable. But the step up, or the extension from that, is to move to what we call a growth mixture model, which is simply just allowing variation within each class. And if you are interested in that, I would recommend you read this paper by Twisk, which has a really great comparison of the two methods using both real and simulated data. And basically that shows that the latent class growth analysis is simpler and in many cases gives comparable trajectory solutions. The large number of things that we have to model if we move to a mixture model can lead to convergence problems, and that's certainly been my experience. The mixture model tends to have an optimal solution with a fewer number of classes because it allows more variation within classes. And an example of this method in the RAIN study is this paper that looked at trajectories of sleep problems. So that's the paper that you can go to have a look at that technique. So in summary, latent class trajectory analysis is a useful and flexible family of techniques for life course analysis, but it should be applied with caution. Detecting subgroups in the sample, they may not actually be real. They may be a function of non-normality in your data or sample-to-sample fluctuations. So it's important that some validity testing is done in terms of cross-sampling or testing the trajectories on another new sample. And it's not always the only or best method for the research question. And it's really important to consider how the level of uncertainty in class assignment, how that can influence further analysis. And Michelle Tew will talk more about that in terms of the probability of membership of classes that is modelled in the latent class growth analysis. The really important thing I always think is to make sure that you look at your data whenever you're doing any kind of model. So I always try to have a look at, for people that don't look like they're fitting the model particularly well, and people that are, have a look at those differences and see what's going on, and make sure that your model is adequately accounting for people that aren't fitting into those trajectory groups very well. And if you do have people like that, you can run sensitivity analyses to include and exclude them from the model and see what the ramifications of that are. So in this case, we had a particular trajectory group, which is the solid line there, and then we're just looking at person by person at how their trajectories fit according to the average line of the group. Okay, so, and here is a whole lot of references on cautious use of latent class growth analysis. So if you do get into it, I would recommend that have a bit of a read of some of these so that you can defend your methods well, apply and defend your methods well. Okay, so I think we won't take questions at this point. I'll hand over to Michelle Tew for an example of an applied application of latent class growth analysis, and then we'll take questions at the end. Okay, so I need to
Hi, everyone. Thank you, Anne. So Anne has given us a really great introduction to trajectory analysis, and for the next 20 minutes or so, I'll walk you through how I've applied this analysis to answer an interesting research question. I wanted to know if total knee replacement patients exhibit specific quality of life trajectories that can be used to guide clinical care. So I've employed latent class analysis to identify these particular trajectories. So before I go on, what I'm wanting to just clarify is quality of life can be measured using quite a few different types of questionnaires, using disease-specific questionnaires or generic questionnaires such as SF12 or SF36 or EQ5D. So I'm only going to focus on those generic questionnaires in my talk here. What do we know about quality of life of patients who have undergone joint surgeries? I have two examples here, which is what is commonly observed. On the left, we have hip replacement surgery from an outcome study where we see large improvement in the quality of life in the 12 months following surgery. On the right, we see a similar trend of knee replacement surgery where surgery results in a large improvement in quality of life, also 12 months post-surgery. However, what we know is that improvement after surgery may not be realized for all patients, and it might be possible that there are two or more distinctive groups with different trajectories over time. And research have also shown that up to about 20% of total knee replacement patients don't actually gain clinically meaningful improvement following surgery. So it might be likely that there is a group of patients that could have different quality of life trajectory to those of the average that we typically see. So in the last decade or so, an increasing number of studies have shown that quality of life are an important predictor of mortality in diseases such as diabetes, and also in the general population. So in this example, here on type 2 diabetes patients, quality of life scores derived from EQ5D questionnaires have shown to independently predict the risk of mortality and complications even after we adjust for standard risk factors. So those reporting higher quality of life were found to be associated with lower rate of mortality and complications. So understanding patients' quality of life and their trajectories can reveal important information on disease progression and outcomes. Quality of life trajectories are also particularly relevant to economic evaluations such as cost effectiveness analysis for a number of reasons. Firstly, scores from quality of life questionnaires can be used to calculate QALYs, which is quality adjusted life years, which are important measures of effectiveness in economic evaluations. It is the area under this curve which is highlighted in blue, that is able to combine morbidity as well as length of life. Second, the standard approach of economic evaluation is to treat patients as an average, to treat patients as a homogeneous group, and cost effectiveness results are usually represented as a group average with a given uncertainty. And on average, we know that knee replacement surgery is a cost-effective procedure. However, it is recognized that in some patients, it's recognized that patients do vary in a number of different ways regarding in the benefit that they achieve from the intervention or in the cost of delivering the intervention itself. So this average that we get may not apply to all patients. So we get those that have high quality of life or low quality of life as opposed to those at average. Third, usually in economic evaluation, extrapolation beyond the study period or available data is necessary. Therefore, assumptions regarding how we extrapolate QALYs or future trajectories is important. So assumptions made can have substantial impact on the resulting QALYs and the cost effectiveness. So the aim of my study was to identify specific quality of life trajectories following knee replacement, and to do this, I've used latent class growth analysis. For today's webinar, will only focus on objective 1, and I will go into details of how I've applied this particular technique and the decisions that were made along the way for the choice of my model. My source of data is the St. Vincent's Melbourne Arthroplasty Outcomes Registry, which is the SMART registry. It's a clinical registry which collects both clinical and patient-reported outcomes in patients that have undergone elective joint surgery at the St. Vincent's Hospital. So the registry is actually a very rich source of data containing information on patient demographics, surgery details, and follow-up data on patient-reported outcomes. The dataset is ideal to answer the research question regarding longer-term trajectories, because now we've got at least 5 years of annual follow-up data which we can use for this particular analysis. So in this study that I've done, it included patients who have had undergone total knee replacement between January 2006 and December 2011. And they gave me about 1,553 patients that were included in this analysis, after we've excluded some of the exclusions that I've applied that are listed on the screen here. So these patients were excluded because in order to capture an accurate representation of long-term quality of life trajectories, some of these patients may be outliers that could sort of affect the trajectories itself, which is why we've excluded these patients. So the registry captures patient-reported quality of life using the SF-12 instrument, and patients are surveyed prior to surgery and annually post-surgery. So the SF-12 responses were transformed into utility values using a published algorithm to get utility values. And the utility value is the general index of well-being used in economic evaluation. 1 is equivalent to full health, and 0 or sometimes negative is equivalent to being dead or in a health state that is worse than death. So baseline and annual quality of life scores up to 5 years post-surgery were considered for the analysis. To run the analysis, I used a data plugin called Traj, which Anne has described earlier. The censored model was selected as the most appropriate for the available data, so I've used that particular type of model. To identify trajectory groups, I followed two-stage model selection process. So stage 1 was to determine the number of classes, and because I don't know how many trajectories there are in terms of quality of life trajectories that could be present, I considered a series of models for 1 to 8 trajectories. And when this was determined, I moved on to stage 2, where I considered the models with different trajectory shapes to find the best fitting one. So this slide shows the various models considering 1 to 8 classes or trajectories. So the question is which one to choose, because there's so many different types of it, and possibly all of them could be viable. As Anne described earlier, there's no definitive criteria for the optimal number of classes. The choice for the optimal model was guided by a combination of factors, which includes goodness of fit statistics, posterior group membership probability diagnostics, and model interpretability. So I looked at the various statistical criteria to assess the fit of the models. Base information criteria is what is commonly used to assess the model fit. In addition to this, I've also used other goodness of fit measures such as the IKIT's information criteria, which is the AIC, posterior group membership probability diagnostics, such as having all groups to display an average posterior probability of above 0.7 and odds of correct classification of greater than 5. The selection aims to balance model parsimony and also to be able to adequately identify distinct patterns that are relevant to my research objective. So patients are then assigned to the trajectories in which they had the highest posterior probability of membership. So this slide shows the AIC and BIC values for each of the models I estimated. For traj analysis, higher BIC or AIC values indicate better model fit. However, what I've found here, or what I've observed, is that the values increases as the number of classes increases. So this can be pretty problematic, which has been identified and discussed by Nagin, where he explains that in such cases, BIC may not be a useful criterion for model selection. So instead, selections should be based on a number of, based on the goal of the analysis, and being able to balance between model parsimony and being able to capture distinct features of the data itself. So to help with model selection, I looked at other statistical criteria described by Nagin and others in the literature to help evaluate the quality of the model. I'm not so sure if I can move these somewhere else. Let's see. So I looked at other statistical criteria to describe, to help me with my model selection. And this included looking at the posterior probability groups, which should ideally be greater than 0.7. I also looked at the log-based factor, where the bigger the value, the stronger the evidence for the more complex model, meaning that we should go for the more, model with more classes. And I also looked at the odds of correct classification, which ideally they should be greater than 5. And there are also other descriptors in the literature which says that perhaps groups should have more than a 10% membership, and also through the visual inspection of the trajectories. So I've got the table here that shows some of these statistical diagnostics. Finally, after considering all these different types of criteria, the model I selected was the 6-class model, meaning that the model with the 6 distinct quality of life trajectories, as shown here in the figure. The box at the bottom represents the proportion of patients in each of these trajectories. So the rationale for choosing my model with 6 trajectories was based on, 1, my research question. So I wanted to know that, do patients exhibit specific quality of life trajectories following total knee replacement? And also based on the statistical criteria, which I went through in the previous slides, and the interpretability of the trajectories of the model. So that was stage 1 of the model selection, which is to determine how many classes I should have in my model. Stage 2 involves choosing the correct functional form to accurately reflect the shape of each of the trajectories. The way to approach this is similar to stage 1, using the same diagnostic criteria that I've previously described. So finally, this was the model which I've selected, aiming to balance between model parsimony and adequately identifying the distinct patterns relevant to my research objective. So this is the 6-class model with the following polynomials for each of the trajectory shape. So the numbers 3, 3, 1, 3, 3 at the top indicates that the first trajectory follows a cubic function, same for the second, fourth, fifth, and sixth. For the third trajectory, the linear function, the third trajectory, which is labeled 1, the linear function was found to be the best fit, so which is the straight-ish green line that we see on the screen, this one here. So the table on the left shows some information regarding each of the trajectories that I've chosen. So the average posterior probability for each of the trajectories was above 0.7, so which is good. And I had the odds of correct classification for for each of these trajectories were above the minimum value of 5, which is ideal as well. To help to describe these trajectories, I've characterized them into 3 main phases. So I've characterized them as pre-surgery, post-surgery improvement, which is the period between pre-surgery and year 1, and also the maintenance, which is the time after year 1. So for example, trajectory 5, which is the orange line, can be described as having low quality of life pre-surgery, followed by a large improvement at year 1. And this large improvement was sustained over the period after year 1 and in the subsequent years. Whereas in trajectory 4, it has a low quality of life pre-surgery, also has this large improvement post-surgery. The effect was not sustained, the effect was a declining pattern in the maintenance phase. So to answer the remaining objectives of my research question, further analysis based on the assigned trajectories were conducted. I won't go into details of these today. So this included calculation of QALYs, which is the quality adjusted life years for each of the trajectories, and also to examine the patient characteristics of identified trajectories, which I've used the multinomial logistic regression analysis. This table shows the calculated QALYs and incremental QALYs. It's quite clear that the area under the curve for each of these trajectories is clearly different, meaning that the QALYs for each of these trajectories are quite distinct. And although trajectory 6 has the highest number of QALYs, which is this gold one here, has the highest number of QALYs, in economic evaluation, we're interested in incremental outcomes. So in this case, trajectory 5 has the highest incremental outcome, which is the greatest gain or the greatest benefit that is gained from the surgery itself. So to summarize the findings of this study, there's evident heterogeneity in quality of life trajectories among total knee replacement patients, which can indicate that perhaps certain groups of patients should be treated quite differently. And from our multinomial logistic regression analysis, we do find that younger patients, younger total knee replacement patients exhibit quite different trajectories to those who are slightly older. So perhaps there might be implications for clinical practice and cost effectiveness of the surgery. And potentially there is scope in using latent class growth analysis in identifying subgroups for health economic analysis. I guess what I'm wanting to share as well is the challenges that I've had with undertaking this particular type of analysis. So one of the main challenges that I find with this analysis was the choice of the number of classes or the best model was not exactly clear-cut. I could not base my model selection on BIC or AIC, which is the case that we've observed previously that it was not particularly helpful in helping with my model selection, where the AIC and BIC just continually increase as the number of classes increase. And I had to depend on a number of different selection criteria and also the research objective itself. The distribution of quality of life data can often be non-normal or skewed, and this can be problematic when fitting the model. However, with this analysis, we had quite a large sample of about 1,500 observations, so I guess it was deemed less of a problem. There are also various ways in which one can approach this particular analysis. Some have included active covariates into their models. For example, I could include sex into the model, which means that having sex in the model, it will play a part in an active part in helping determine the trajectories. But in my model, I've only included quality of life as the variable in which I wanted to look at. So because complex models, when I include more covariates in the model, it can have problems in converging or running the model itself. And although there are a lot of resources on latent class analysis, and Anne has, through her presentation just now has been really helpful in, providing loads of resources, and also in helping me, pointing me in the right direction with all the different types of resources. Unlike regression analysis, there are loads of resources, so there is much less on this type of analysis, which meant that it just took me a little bit longer to find solutions and understand this type of analysis. So just acknowledgements, and yeah, that's it. Thanks very much. Any questions? Michelle, do we have any questions from the audience?
Thanks, Michelle and Anne. At the moment, we don't have any questions, but I'd like to remind everyone that if you would like to ask your question, please make sure that you raise your hand. For those who can't ask a question because you don't have a microphone, you are more than welcome to click that Q&A box on your panel, either at the top of the screen or at the bottom of the screen, and you can type in your questions for Michelle or for Anne. Anyone? Any questions? No?
Michelle, can I say something? Yeah, the content is quite overwhelming probably, and not fully appreciated until you actually want to do something. So both Michelle Tew and I will be willing providers of resources should you, any of the participants, want to try out some of these techniques on their data.
Yeah, and these slides and the links that you've provided in your slides, they're going to be available online on the OPUS website, where we store all our webinars. So you'll be able to refer back to it. We do have a question from Michelle. Michelle Dowsey. Hi, Michelle.
Yes, hello. Can you hear me?
Yep.
I was just curious to know, like we've got a lot of time points. If you had even more time point, does that make it more complicated, or is it better? Do you know what I'm saying?
So the question was, is it better to have more time points or less?
Yeah.
More is better. Yeah, it means you've got a lot more information and you've got more kind of support to model the time structure. Yeah.
Just because with Michelle's work, the one thing we don't have is what happens in that first 12 months.
Yes.
And just wondering what effect that would have if we did have, 3-month and 6-month time points.
Yes, because if you've got additional variability there, then you may have more trajectories than you've observed.
Right.
Yeah.
So the potential impact is it would provide more patterns or more trajectories. Possibly.
Yeah.
Right.
Yeah. Yeah. If there was heterogeneity in how people changed over those first 12 months, that's not factored in the 0 to 12 month change.
I suppose, Anne, would there then be a trade-off? Because sometimes if you want to include more time points in it, then you'll probably lose more patients, probably get a smaller number of patients who have a longer follow-up than those that have a shorter follow-up. So I guess there's a trade-off between the number of patients that you want to include in the analysis or the longer time frame that you would like to look at.
Yeah. That is a consideration, except that because it's using maximum likelihood estimations, you can still include those people without the longer term follow-up. So they will, you're not limiting your N by not having people that don't have all the follow-ups. And what you'll see happen is for the people that don't have as many follow-ups, their probabilities of membership are more fuzzy than people that have all of them. And so then you can do sensitivity analyses by probabilities of membership to see how robust your findings are for those people that have less data. Yeah, but I think the benefit of having the more, not necessarily longer time follow-up, but more granularity in the time that you have is useful because you can better capture patterns. Yeah.
But doesn't that then rely, because if there was, if that resulted in more patterns, more heterogeneity, then you would think that you would have to have a bigger sample size. Otherwise, you might get groups that have got numbers. So isn't that a kind of like weighing that up as well?
Yeah, possibly. I mean, your fit statistics are also based on model parsimony. So, you know, if you've got small groups that, you know, your fit statistics will probably support the smaller class model anyway. Do you know what I mean? So, yeah, if there's more patterns identified that are worth the extra parameters, then your fit statistics will tell you that. Yeah, does that make sense?
Thanks, Anne.
No worries.
Another question from Christian.
Yeah, hi Christian.
So he's written, what sort of numbers do you need to consider using this type of analysis?
Good
I'm not
question.
sure, Christian, for Anne and Michelle, but let's go with both.
That's a very good question, Christian. And the answer is there is no definitive answer. It depends on a lot of things. It depends on the number of time points you have, the complexity, the underlying true structure. So there are a few studies that have done simulation power analyses by creating you know, particular structures and then seeing how many people that you need to identify that structure. And so probably the rule of thumb I tend to go with is about at least 300. Yeah, but that can be pretty variable depending on the levels of complexity, the type of variables you've got, the number of time points you've got, the amount of missing data you've got, and so forth. So not a very clear answer, and it's a kind of it's a field that's always developing. So there is, will be, you know, papers coming out regularly on sample size in latent class analysis.
So Sam has a question for me. So she asked if I'm able to test a hypothesis about, for example, the factors that are driving the decreasing quality of life trajectory. So following the identification of the different types of quality of life trajectories within my patient groups, I have undertaken further analysis to try and understand what sort of clinical characteristics these patients have for each of these trajectory groups, which I've done multinomial logistic regression. So we find that the trajectories in which patients have great big improvements over time and are able to sustain the improvements are those that are of younger patients and less comorbid patients. So I was able to test some of these hypotheses with regards to, you know, what sort of factors, what sort of patient characteristics that predispose this patient to be in each of these trajectories itself. So that's something that I'm working on with Anne, Michelle, and Peter. So there is potential to identify some characteristics of these patients.
Yeah, could probably just add there that we didn't have time to go into the complexities and subtleties of modelling the time varying and time non-varying covariance of membership with the trajectories, because and it is quite complex and there's a number of ways to do it, but definitely it's usually the ultimate goal is to find out, you know, what predicts membership of a certain trajectory, or if other things that vary over time can change the trajectory course. So a lot of the resources or the papers that I have given will put on the OPUS website will be around that, so that you can go and further explore that.
Michelle again. Anne, is there any possibility that you could take, would need to be a fairly large, but like the data from a randomised control trial and apply trajectory analysis to see if you haven't observed difference between groups, is there subgroups within your groups? You know what I mean?
Oh yeah, no, definitely. And I think there is quite a bit of work that's being done in that area. I think that the Muthen, you know, the developers of M+,
yep,
have quite a bit of stuff on the application within the randomised control context. Yeah.
Because I could see some added value applying it, although often within RCTs your numbers might not be big enough.
Yeah, that's the issue. Yep. Yeah. That's usually the issue. It's usually a more sensitive analysis to do a mixed model with treatment group as the predictor.
Yeah.
But I guess what you're asking is if there's groups of treatment response, so they're latent classes of treatment response there with a distinct separation between responders and non-responders, for example, rather than, you know, just a normally distributed treatment response. Yeah. All right.
Okay, I think that's it for the questions. Yeah. If you do have any other questions, once we close this meeting, you can always send an email to Anne or Michelle. And again, the webinar is going to be available online on the OPUS website, and I'll be sending the link out to everyone. But that's about it. Thank you very much for tuning in. Hope you enjoyed it.
Thanks, everyone. Thanks for listening.
We'll see you next time.
All right. See you.